Hello, this is the next video in Unit 4, Relations and Functions. Called linear functions, including graphing a line. Okay, so we're dealing with functions today that produce ordered pairs that lie on a straight line. So ordered pairs lie on a line when graphed. So you're going to see a lot of graphing today, you're going to see a lot of tables, and I'm going to throw out some vocabulary for you. So first of all, I'm going to start with a just random function that will produce a straight line. F of x is 2x plus 3. I'm going to graph it over here in a second, but first I obviously need some points. So I'm going to make a table here, and I'm going to pick some values for my domain, and I'm going to pick these values and plug them in. Remember, this is the domain, and if I plug them in, I get these values. Okay, I did these ahead of time. So I have a variety of abscissas and a variety of domain values, and I'm going to plot all of them. Oops, that should be here. Okay, ignore that one. Okay, so I plotted as best I could, and I do get something that resembles a straight line. Now I want to point your attention to a couple of points that are important in every line. One of them is where the line crosses the y-axis. This is called the y-intercept. That's where the line crosses the y-axis. And this point here, which is not one of the points I plotted, but we know it crosses the x-axis, is called the x-intercept. Now I happen to have the coordinates of the y-intercept right here, 0, 3, so I will label that. Now, if I were interested in the x-intercept, I can find it because I know that the x-intercept will have an ordinate of 0, because every point on the x-axis will have an ordinate of 0. So how do you think we're going to find the x-coordinate of this x-intercept? Well, since I already know the ordinate is 0, I'm going to plug 0 into f of x. And then solve this equation. So when I solve this, it's negative 3 over 2. Unfortunately, it's a fraction, but no big deal. So that point is located at negative 3/2, 0. That is my x-intercept. So this is my y-intercept, and this is my x-intercept. Almost every line in the universe has an x-intercept and a y-intercept. There are a couple cases where you don't have both. In the case of a vertical line, if your function happens to produce a vertical line, you'll see that it has an x-intercept but no y-intercept. In the case of a horizontal line, there is no x-intercept. But if the line is slanted in any way, there will be both an x-intercept and a y-intercept. And something I want you to think about is why does this equation produce points that lie on a line? Because not all functions turn out to be lines. Some turn out to be parabolas, some turn out to be other shapes. Why does this turn out to be a line? Is there something recognizable in the equation that tells me, oh, this is going to turn out to be a line? I'm certain of that. This is the general form of this example. Something times x plus something. That's the form that this was in. I'm going to show you another example now. Just keep this on the back burner for a moment. Okay, so now I have a different function. I'm using f of x, but it's a different function. It is negative 1/2 x minus 3. Notice it is in the same form. It's something times x plus something. It's plus negative 3, which I have changed into minus 3. So again, table. I'm going to pick different values for my abscissa. I'm going to pick 0, 2, negative 2, and negative 6. And if I do that, I get these values. And I will plot it over here. That's 0, negative 3. That's my y-intercept. Negative 4, 2, negative 2, and negative 6, 0 is my x-intercept. Okay, so I'm getting a line again. So that's twice that I've had something in this form and I got a line. So this is the magic formula. This is a linear function. All linear functions can be written like this. There are other forms of a linear function, but for now, memorize this. Mx plus b is the general form of a linear function. And this linear function gives us an x-intercept of negative 6, 0, and a y-intercept of 0, negative 3, and then there are a couple other points that we plotted. Now, if I wanted to minimize the amount of work that I perform to graph these lines, I don't have to plot that many points. Here I plotted 7 points, here I plotted 4. I didn't have to plot 7 points to know where the line was. I didn't even have to plot 4 points to know where the line was. What is the minimum number of points I need to know where a line is located? Just 2, right? If I had just plotted these 2 points, that line I would have sketched the same line that I just sketched for you. If I plotted these 2 points, same line. Or these 2. So we just need a minimum of 2. Now, It is important, though, that we know where the y-intercept and where the x-intercept are. That's why I highlighted them in both lines. So you can kill two birds with one stone. The stones being, where's the line, and the second stone being, what are the x and y-intercept. You can kill both of those stones by, in your table, finding the x-intercept, or this is the y-intercept, finding the y-intercept and finding the x-intercept. That's 2 points, which is the minimum number of points you need to graph the line, and these 2 points happen to be the y-intercept and x-intercept, so you know that information as well. Over here, if I had just plotted 0, 3 and negative 3, half 0, that would have been enough to know where the line was, and I would have known where the y-intercept and x-intercept are. Okay, so now I'm going to do that. I'm just going to plot 2 points. I'm going to find the y-intercept first, which I know is on the y-axis somewhere. If a point is on the y-axis, then I know the abscissa has to have a value of 0. So whatever I get when I plug in 0 here will tell me where the y-intercept is. And that'll be 4. So I know the y-intercept is right here at 4. And then if I want the x-intercept, that's going to be a point somewhere on the x-axis. The ordinate for that point will be 0. So I plug in 0 for f of x. And just to make sure I'm doing this on paper. And that'll give me negative 3/4, which will be about here. And there's my line. 0, 4 is my y-intercept. Negative 3/4, 0 is my x-intercept. Now, what if you make a mistake? Maybe I accidentally put negative 4/3 here instead of negative 3/4. Well, if you have any doubt about where this line is, you could just plot a third point, an easy point. So I'll just plug in a 1, and I get 7, 1, 7. So that'll be somewhere up there. So if I had made a mistake and put this x-intercept in the wrong place, maybe to the left, maybe to the right, after I plotted the third point and I connect the dots, I would have noticed, wait, this is not a straight line, because I would have been forced to veer off to hit that other point that's in the wrong place. So that would tell me that something here is wrong. Probably one of these 2 first points I did was wrong. So then you can go back and correct yourself. But if all 3 points lie in a straight line, then you know that you did them right. And you probably don't need to plot a 4th point. It helps if you have graph paper, so you don't have to draw all these hash marks that I've been drawing. And also if you're kind of messy and you don't plot points accurately, graph paper will help you do that. Okay, that's basic graphing of a line. I do want to show you one example of why intercepts are important. So let's say this is the graph of the amount of money you have to pay a taxi to go somewhere. And the number of miles that the taxi travels is on the x-axis, and the amount of money you have to pay is on the y-axis. And this is the y-intercept of this graph, which is at 0, let me just make it 0, 8. and then I'll plot a point here, 3 comma, we'll just make it 12, 3 comma 12. Okay, so what does this tell you? Well, it tells you that the more miles you go, the more expensive your taxi fare is going to be. That makes perfect sense. What does the y-intercept tell us about this? Well, this point is at 0.8. So that means before the taxi even starts driving, you have to pay $8. So that's a fee that's automatic when you get in the taxi cab and tell him to go somewhere. You're going to pay $8, even if he goes a few feet, you're going to pay that $8. So that's the significance of this, the y-intercept in this particular situation. There's an $8 fee. And I put this second point here so that you can see, or at least calculate, how much money you have to pay for each mile that you go. So after 1 mile, 2 miles, 3 miles, the fare is now a total of $12. If you had only gone 1 mile, it would be whatever this is. If you'd gone 2 miles, it would be whatever this is. So that means there's $4, because that's the difference of 12 and 8. There's $4 more dollars that you had to pay because the cab went 3 miles. So this is a distance of 3 miles. There was an increase of $4. So for every 3 miles, you have to pay $4. So there's a relationship between the money and the miles, and it's 4/3. It's a ratio of 4 to 3 dollars to miles. That's the way this cab works. And that's how linear functions can help us understand different situations. Okay, so next time we'll be talking about slope and equations of lines.